Okay, let's talk about instantaneous rates of change, and we're going to do it as they are represented with limits. So the first thing is you really have to understand limits, or I'm sorry, slopes, and slopes in their different representations. So I cannot stress this enough. Do not move on to the limit part until you are comfortable with the slopes. All right, so the idea is I'm only going to do one example, but you could make up as many examples as you want, and you need to keep doing them until this is just second nature. All right, so do it until you can't get them wrong. That's the idea. I cannot stress that enough. All right, so let's talk about slope. So my first representation for slope is I'm given 2 points, right? And one of them's given just as a constant, the other is a variable. So when I say that, I mean one of them would be given, so this is a constant a, so it means in my problem here, maybe they tell me that x is 4, right? Or x is 2, all right? But somewhere they give me one of the x's. And then the other x I leave as just a variable, right? And when I say the variable, it means that this actual point takes on all possible values. So it could be here, it could be down here, it could be up here, it could be anywhere, right? But this one is given, so it's going to always be locked there. And this one is a variable, so it could be anywhere, all right? That's how we kind of do that weird stuff. So now the slope here is just your normal slope. Change in y over change in x. And our y's in this case are represented with function notation. And that's another thing you have to get used to is a function notation. So y2 minus y1, y2 minus y1, all over x2 minus x1, x2 minus x1. Okay, so that's my point is you cannot move on to limits until you understand these things. Until you can really see that f of x minus f of a all divided by x minus a is just a slope. And it's a slope of a given point and then a variable point. All right? Okay, our second one is I give you an actual point again, but I don't give you a second point, I give you a change. So now again, my f of a is locked, this will not move, but I do this h, I say, well, only go h away from a, right? And so now h, since it's a variable, if I make h big, then the point actually goes down this way. If I make h smaller, the point goes this way. If I make h negative, the point's over here. So there's a lot of things I can do with h. All right, so the last one is I move that point around by making it variable, f of x. Now I move the point around by making a little change in h. And h will move that point around. So my slope now is the same thing, change in y over change in x, so f of a plus h. And now x2 minus x1, you'll see the a minus a will just be left with h. So this is the slope that you'll see, all right? And it really is, even though it doesn't really, you can't see it from here, it really was x2 minus x1, all right? Okay, so that's a second way we can do represent a slope. Give me a point, and then I'll represent that second point by a change in h. Okay, the third way is, let's do a variable point, so not a given point, and then we'll have a little change also. So now my f of x, this is not a fixed point. This point can move anywhere I want, depending on what x is. And now my delta moves this second point all around based on where this point is. So now everything's variable, right? I don't have anything locked in, right? And that's the beauty of this. The first two, we were locked in on that a position, x equals a, right? So it only worked when I have, whatever a was given. This works for everything. This will be a general equation, which is very nice, right? But the slope's the same. So x2, or I'm sorry, good Lord, y2 minus y1, right, which is right here. And then x2 minus x1, and then you'll see the x's are gone, they cancel out, so I'm left with delta x. And again, it's not easy to see, but this really is x2 minus x1. All right, so those are our three representations. Oh, and I'll go back. I'm going to put these in our notes after I do this example. But these are the three you have to memorize and really start being comfortable with. Okay, so first, let's do an example. So I want to write and simplify equations for the three slope representations, right? Given that here's my point, x equals 2. And again, that'll be used for the first representation and then the second, but not the third. Because remember, the third was a variable x and then a variable delta x. Okay, and now here's my function. All right, so let's do our first representation. Change in y over change in x. So f of x minus f of 2 all over x minus 2. And I know what f of x is. It's x squared. So I can do my substitution. So f of x is x squared, so f of x turns into x squared. F of 2 is 2 squared because substitute in 2, and I get this. And now I can simplify. These all will be simplified. So I get x squared minus 4, then I'll get x squared minus 4 becomes x plus 2x minus 2, and then they divide out. So the first slope equation, right, is x plus 2. All right, now what does this mean? So let's go here. So here's my graph of the function. All right, so here is x squared. We did x equals 2, which is this point right here. So let's say I pick the second point down here, 1, 1. Well, the slope from these 2 points is 3, right? So 4 minus 1 and 2 minus 1 would be a 3, all right? Well, and the slope from this point to this point is actually 1. So this equation should give us those slope values, and you'll see they do. So if I go from 2 to 1, my slope is simply the x value plus 2, and the x value is 1, so 1 plus 2 is 3. And you see it gave me that slope. And then my 2 to negative 1, the x value is negative 1, so negative 1 plus 2 is 1. It gave me that slope. So this actually is an equation that gives me the slope to any x value you want as long as you start at 2, 4. All right? That's a weird thing to kind of internalize. But that's what that x plus 2 means. I started at 2, 4, and then I can tell you just by giving if you give me the x, I can tell you what the slope is. Okay. All right. Let's do our second representation. So now we're doing our h, right? Our plus h. So now it's f of a plus h minus f of a. Again, go back to the equations we had before, and you'll see what's going on. This is the part that I can't stress enough. You have to practice this until you're just second nature. Otherwise, the limits aren't going to make any sense. All right, all divided by h. And same kind of thing now. I have 2 plus h. I'll plug into here. I have 2 that I'll plug in, so I'll do my direct substitution. Then I'll do my algebra, so I'll distribute out to 2 plus h times 2 plus h. And now you'll see the 4s divide out or cancel out, right? And that always is going to happen in this situation. So you'll see on the second representation, the third, you're only going to be left with things with h's. If that doesn't occur, you did something wrong. All right? Okay, so the 4s are gone, so I only have h's. You'll see I have a common h, which I can pull out, and then the h's divide out. And now here's my slope representation. So I'm saying that the slope here is now the number 4 plus some h. All right, let's see how that works. So let's go back to our picture. So again, we have to start at 2, 4, because this was all based on x being 2. And you can see a delta now. This is suggesting you tell me how far away from this 2 value you want to go, and I'll tell you what the slope is. And you can see that works out perfectly. So if I go from 2, 4 to 1, 1, from 2 to 1 is a negative h. I'm going 1 in the negative direction. And so 4 plus a negative 1 is 3. And you see that's how I get my slope. So this actually is the exact, and they had to be the same answers, right? But this now will tell me the slope based on the change that I want to do from this 2 value, right? Okay, so if I go from remember, we always have to start at 2, 4, or 2, because that's how we set this up, the 2's. So if I go from 2, 4 to negative 1, 1, 2 to negative 1 is a change by negative 3. So I'm going 3 in the negative direction. And you can see, I have a negative here, which it shouldn't be. I need to change that. That needs to be a positive. So it should be 4 minus 3, right, equals 1. All right, so scratch that out, 4 minus 3. All right, but it is a 1. Okay, so now let's do our third representation. And now here's our x plus delta x. So now I'm freeing up that a point. I'm going to just have, it doesn't matter where I am now. I'm not at 2 anymore. I'm just at x. All right, so do this, and same thing. Direct substitution, x plus delta x into this equation, and then x into this equation, and I'll get those. Do my distribution, and I'll get an x squared. So x times delta x is x delta x. So when I FOIL those out, I'll get this. And then notice the x squareds will cancel out. That will always happen, just like the h's. I'll only be left with delta x's. All right, and again, if that does not happen, you did something wrong. All right, so same thing as like the h. So now the delta x are in common. Now the delta x's divide out. And now I'm left with 2 times x plus delta. And you can see this is our this is our h equation. So when x is 2, 2 times 2 is 4, 4 plus a little bit of change. This is the same thing, except now I'm not bound by that 2. This, you tell me any x, and this will work. So if x is 1, then it's 2 plus delta x, which would be 2 plus h. Right? So that's what this does for us. It doesn't lock us into that x, that 2. All right, so let's see how this works. So now since my 2 is, or my x is, can be anything, I'm going to have to figure this out by plugging in this 2. And you'll see once I do that, the deltas are the same as the x's, or I'm sorry, the h's. And now you'll see, though, I have to figure out this first part because I need to plug in an x. Right? And that's what this representation does. It frees up that point. I don't have to be at 2 anymore. So I could do all this work again, and I can pick x equals 1 and do 2 times 1 and then figure all that out. All right, so I can move this around everywhere, and that's the beauty of this one. All right, okay, so again, you can do the same thing, maybe change the numbers or change the equations, maybe do, I don't know, x cubed is a little too much, but maybe do 3 times x or 3 times x squared, but keep playing around and practicing. All right, but for the notes, though, you should have these 3 representations in your notes. All right, so the first one is, right, it's going to be locked at a point. So I have one point that's variable and one point that's locked. Then I have, same thing, I have one point that's locked and one point that's variable, but it's variable by, it's going to be a difference. It's going to be a little change in x. And now here, all points are variable, and how I get to that second point is with this change in delta x. All right, so this is how I get to the second point, and this is how I get to the second point. All right, okay, so put those in your notes. All right, now let's talk about rates of change. So average rate of change is something you already know. It's simply just a slope, right? And what it really is an average. It's the amount one quantity changes with a 1 unit change in a second quantity, all right? And that is just a very complex way to say slope. So here's my line. I have 1, 1, 2, 3. The slope is 3 minus 1, 2 minus 1, so 2 divided by 1. All right, so what this suggests is every time x increases by 1, y increases by 1. Every time x decreases by 1, y decreases by 2. Oh, I think I said 1 first, yeah. But every time x increases by 1, y increases by 2. And if x decreases by 1, y will decrease by 2. So that's what this means. To have a slope of 2, it means on average, every time the x does something by 1, the y does something by 2. That's what it really means by average. All right? So you can see if we're going to find the average rate of change for a function, it's simply just a secant line. So if I wanted to find the average rate of change of this function that I put in red, then the average rate of change between those 2 points is 2, right? It means that from here to here, on average, every time I go 1, I'll have to go 2 to get to that point. That's what it means. And if this were farther away, maybe it would be I go 1 and then a little bit, then 1 and then a little bit. So it doesn't, so it still is just an average rate of change. Okay, so if you want to find an average rate of change of a function, you just find a secant line. That's the deal. All right, let's talk about instantaneous rates of change. So an instantaneous rate of change is simply how a single point wants to behave like an average rate of change. Right? So it's at the single point, at this one point, where does it really want to go? What line does it want to be on? That's kind of the idea. So it's something like this. Let's say I have a single point. This green point really wants to follow this green line, all right? And so now I'm going to do a slope. I cut it off a little bit, but I'm going to do this 2, 4 up here. So the slope of this green line is 3, right? So it means on average, right, same kind of thing. On the slope is average rate of change. So on average, it means that every time the x goes by 1, the y goes by 3. So 1, 3, all right? The instantaneous part now is if I do it for a function, the instantaneous rate of change is actually the slope of the tangent line. So now you'll see it's different. So now I don't have 2 points on this function where I cross a secant line. I only have 1 point, and the green line is a tangent line. All right, and so now here's the deal. The instantaneous rate of change of this 1 point is 3. This point really wants to act like it's on this green line. And so as soon as I move a little bit in the x direction, it doesn't follow the green line, it sticks to the red line. So something happens to it to force it to the red line. But the idea is, as an instantaneous rate of change, this is how it wants to act. It wants to act on that line. All right, that's the instantaneous part. So average is all about secant lines. Instantaneous is about tangent lines. All right, so let's find instantaneous rates of change. Since we know it's all about slopes of lines, right? And that's the point here. Even a tangent line has a line itself, right? So even instantaneous is on some kind of a tangent line. Well, I'm going to have points here, all right? So what we can do is we can estimate a secant line. So that's the blue line. And here is my first, you can see where this is going, right? Here's my slope representation for a given point and a variable point. So the actual average rate of change is the slope, f of x minus f of a all over x minus a. That's the blue line. The blue line will turn into the red line as soon as x starts to approach a and actually hits a. So as x turns into a, the blue line turns into the red line. And how do we do that? We do it with limits. So that's where limits come in. So the instantaneous rate of change, the slope of the tangent line, is the slope of a secant line as these two terms come together. That's the deal. All right, so that's how you turn a secant line into a tangent line. You find the limit as you collapse that space between those 2 points. All right, and you'll notice we had 3 representations, so we have 3 of these as well. So same kind of thing. Here's f of a, and now to find my second point, I have a little change in of h, right? And so now the average rate of change is simply the slope of the blue line. And now how am I going to make the blue line the red line? I need to condense that or collapse that h to 0. So that's what the limit is. The limit will take h to 0 of the secant line slope. All right, so that's how we find tangent slopes. We collapse secant lines into tangent lines. All right, and our last one is our variables. So remember, now it's not a fixed point. There's no a here. This could be anywhere. And then this is always a delta x away. All right, same thing. I want the average rate of change of the blue line. That's just the slope of the blue line, the secant line. And then how do I get the secant line to be the red line, the tangent line? Collapse this delta x to 0. So its limit as delta x goes to 0. All right. So these instantaneous rate of changes are just limits of slopes. That's all they are, of slopes of secant lines. All right. Okay. So in your notes, you want to write these 3 forms. So these are the 3 ways that we represent instantaneous rates of change, right? Which are in fact slopes of tangent lines. All right. And this one, like we did before, this locates a point, and then the other point's variable. This locates a point. And this slope, though, kind of gets our second point by having a little change in h. And our last one here is just all variable. This is not located at a point, right? So these 2 are only good at a point. This one will give you an equation for every point. That's the beauty of it. All right, and the last thing is, just as a nice little note, these are all indeterminate forms, right? So if you were to do direct substitution, every single one of these would come out to be 0 divided by 0. Which is why we had to spend time discussing limits of indeterminate forms. All right, so it's just something to note. All right, that is it.